at that, I've got a long way. The other thing that came up, again, just on the basis of need, so Mega, who will give a talk remotely, I think. But so we're doing this part, these tidal disruption events, so you throw a star at a black hole in the GR code, so we can get the exact solution for the Kerr or Schwarzschild metric around a black hole, and we do fluid dynamics in that metric. But one of the things we wanted to do is, this is a tidal disruption event, which is a partial TDE, where the star survives the encounter. And that surviving core is super expensive in the simulation because it's like a dense, horrible thing. And so what we wanted to do is replace that with a sync particle, which if we were doing the non-GR thing, that would be a trivial step. You just replace the dense bit with a sync particle. But it meant that we had to think about, okay, how do we, and we deliberately switched them off before, how do we think about sync particles in the GR code? This has taken us down a certain rabbit hole that's gone a long way. So for example, the sync particle by itself has to follow a geodesic correctly, so it has to do the orbits in the GR metric. But in a couple of recent projects, we're starting to think about what if we have a binary, for example, if you have the regular sync particle interactions, and that gets close to the black hole, how do things go? So for TD, it's not too bad because mostly what happens here is the self-gravity becomes unimportant once you enter the tidal radius, and it doesn't matter if you do it badly. But if you have a thing that is just held together and you've got a binary then playing close to your black hole, then the actual physics of that becomes a bit messy. So we've been working on that. We're trying to work on a linearized gravity scheme at the moment, so we can make the binary go at arbitrary speeds and still get the correct approximation. But you'd become, actually, so Mega's submitted a paper on some of the methods on that, which is, so you can't, post-Newtonian's okay, but you can't use it when the velocity gets close to the speed of light. So when the velocity gets close to the speed of light, you'd like a small perturbation, but it breaks most of the approximation methods. So finding a good approximation for like stars that aren't destroyed close to a black hole is kind of messy, but we've been working on it. But sync particles now work. That's a sort of invisible change, but it took us a lot at the back end to make sure we conserve all the things when you're running sync particles in GR. But the effect of that, for example, is we could go on, this star's been destroyed, it's carrying on, and then we can follow the subsequent accretion onto the black hole. And actually the partial TDE turns out to look a lot like a regular TDE in the sense that you start to accrete material into the black hole, you smother it, and that just looks like a sort of optically thick optical transient, which is what all TDEs kind of look like. So a couple of improvements on the GR code as well, partly from my travels, is the Kerr-Schwarzschild metric. We just didn't have in the code before we had it in Boyer-Lundquist coordinates. And the advantage of Kerr-Schwarzschild is you can actually simulate stuff just inside the event horizon. And that's helpful, so the coordinates cross the event horizon. And that's kind of helpful because you can swallow stuff when it can't influence the outside. So that's something that's quite common in GRMHD codes. We just didn't have it as an option. Now it's an option. And sort of related to that, and actually the reason why that was put in is because there's now also the possibility to do two black holes. So there's this really nice thing from these two people, Comey and Ressler, where you can add two black holes and they kind of patch two Kerr metrics together in a way that is an approximation, but it's not bad. So obviously what you miss is the gravitational wave emission from the two things. But you get, when you click close to either black hole, you get the Kerr metric, and these are patched together really nicely. All right, so that's a nice thing. And just a real dumb simulation I did of just stretching a star into two black holes, just to show you that it works. I'm going to speed up, but just some flash advertisement for what you're going to see later in the week. So dust formation is something we've been worked on very actively, and that's really in the context of these AGB stars. So David's going to talk, Owen's going to say some things as well, Camille's working in this area. But really it's all driven by these companions being observed in AGB star winds. And the dust really seems to form in the wake of the companion, and that's really interesting observationally, which Davo will tell us about. But there's lots of effort going into this area in terms of chemistry and dust formation. So, for example, one implication could be that the companions are actually setting the mass loss of AGB stars, and if mass loss of AGB stars is kind of the whole game for AGB stars, so that could be quite significant if true. Yes, so the one on the right there is just the amount of dust formation going on. All right, radiative transfer. I mentioned this at the last workshop, but this is really like having diffusion of radiation in the code, so we're using the flux limit diffusion approximation. something we've used in star formation for a long time, but it hadn't been ported to Phantom. So Mike has helped port this stuff, and Mike has published the first paper using it. So for example, you can do a shock tube where the radiation actually leaks, and so you end up with sort of more like an isothermal situation, or you can trap the radiation depending on the opacity. So you can have something resembling radiation transport, which is correct if the diffusion approximation is correct, and the flux limiter just limits the diffusion to not go faster than the speed of light. So that gets us on the road to radiation hydrodynamics, and Mike's published the first paper on that, which is in the context of common envelopes. And where we'd really like to go with this is into stars that pulsate, and like the radiation comes, there's some heating coming from the central source from nuclear burning, so you can sustain convection in the envelope and be able to simulate that convection would be great. The other way of doing radiation is we couple with MC-FUS. MC-FUS is a Monte Carlo radiative transfer code, so it's multi-frequency, nothing wrong with the radiation approximation. It's really expensive, so you can't run it every time step, but you can run it pretty frequently. And that means, for example, in a disk, you can really have the star irradiating the disk, reaching, we assume radiative equilibrium at the moment at all times. You can really have the temperature in your disk set by that irradiation and responding live to that. So Sal is going to tell us some of the really nice applications of that, actually. So it's kind of complicated procedure, but it's all the magic is inside MC-FUS. We just call it and say, what's the temperature, please? And it gives us back the temperature by solving a bunch of complicated equations to do with photons. But that's the other way we have of doing radiation, first used by Beck in 2020. So just to remind everyone that this exists, because it was a really nice application. So we've got a binary star irradiating the disk. But of course, binary stars can also warp and break a disk, and that can cause shadowing on the outside, for example. So you can do all that sort of stuff self-consistently. So we're always looking for fun applications of this stuff because it's a really nice piece of toolkit. And Pedro, I think, is going to give a talk as well. He's going to tell us some of the other applications as well. I'll speed up. So this is one from Sal. Sal will tell you more later. But again, so if we can do self-gravitating disks with live irradiation from the central source, actually turned out to be kind of obvious, but expensively obvious, in the sense that if you just have a constant source of radiation, which you do from a star, basically your gravitational display just dies off with time. That led us down a whole interesting rabbit hole. Actually, that was a Phantom workshop project, which became a real paper, and led us down a whole rabbit hole of actually then we shouldn't be doing cooling for gravitational stability. What we should be doing is adding mass to the disk, which is how it happens in the real universe. So there's actually been a few papers since then. So Cristiano published one where we started adding material in a ring instead of trying to cool the thing down. So we're adding material in a ring, and then the disk becomes gravitationally unstable because you're adding mass to it. So that's really fun, and it's quite different to this kind of fake cooling picture. That this is more like what's going on in the real universe. You get mass added from the environment, the disk goes into gravitational stability. You can get the similar kind of structures. So this kind of general idea of adding influences from the environment, Josh will tell you more about as well. So AB Auriga was one of the most beautiful protoplanetary disks that was speculated to be gravitationally unstable. Where there is observed infall onto the disk, so it's pretty well known that there's mass coming in. So we did it, there's some nice new modules now to inject those observed infalling streamers onto a disk in a simulation. And you can see Josh did a pretty, well, you can judge his talk later, but Josh did a pretty good job of reproducing this object in simulations. So Anna also, I think you'll hear from, got back, who's just submitted a PhD thesis. Congratulations, Anna. So this is the same kind of idea applied to Roche-Loeb overflow. So this is also really exciting because there's lots of things you want to do with Roche-Loeb overflow. The dream is already in Anna's paper, which is a sketch by Jack. What we'd like to do is this whole thing, and this is like potentially on the cards here. So Julian's been working on this along with Beck. So one of the things that makes that possible is the adaptive particle refinement that's been mentioned at previous workshops. But that allows us to refine near the surface of the star, and there's some very good progress on that in the last couple of weeks that I hope we'll see some nice movies out. Maybe you could win the movie competition. And so actually one of the applications from the last workshop was in tidal disruption events. There's kind of a problem where we're trying to smash a star from a black hole, but just as the star gets shredded, there's a very hard to resolve shock that happens at pericenter. And this has caused a lot of angst in this field where people think you shouldn't do TD simulations because you'll never resolve it and you'll need 50 billion particles and we're never going to do that ever. And actually we did it. So last workshop was like, we should use APR, and why don't we try using APR? And actually this went from idea to simulation, so light is another thing we've been working on. But actually, so this paper came in the last year, it was an idea at the last workshop that got written up as a letter and is a real thing, and actually caused a real ruffle in the field because it's like, actually you can converge on this thing. So you can see so this is about 10 million particle simulation, and we started doing APR on it. So Fitz went absolutely nuts, 16 levels of refinement. So that is equivalent to 4 by 10 to the 10 particles. And you can, well actually equivalent to 10 to the 12 particles is the highest one. So you can really see the amount of energy dissipated in this changes with resolution, but at some resolution actually converges. And so you can get at what the true answer is. So that, in fact, we've even attracted criticism, a whole paper criticizing our paper, which is the highest praise you can get in science. So that's good. I mean, and actually a few people got scooped by that, and we're like, oh, crap, you've scooped us trying to do things. And so this is actually a really nice result that came out of the last workshop. So congratulations, team, on that one. Another little thing, I should stop talking, but something I worked on, especially with the visit to Grenoble last year, was this kind of idea of interacting disks. So one of the things you often see observationally is you've got an observed separation, you've got an observed difference in the systemic velocity. So you know 4 parameters of the orbit, but there's several that you don't know. So we worked on a little cute setup thing in the orbits module where you can run a simulation that will always stop at the observed separation and after observed velocity separation. I'll just do all the background work for you. And so that's quite fun, so you can run lots of scenarios, but the scenarios will always finish with the observational constraints satisfied. And then you can go nuts running like possible things that could interact and give you the right thing afterwards. So there's still a paper in progress on this HH48 object, but it's quite a general idea of reconstructing any kind of car crash that goes on in the universe. Something you might not have tried, but you might like to try during the week. That got submitted last workshop, a workshop ago. Fitz is nodding and laughing. If you touch a file called egg.txt while your phantom simulation is running, you get some nice surprises. What's next? Well, our game is always really to enable that simulation observational comparison. I'll just flag a couple of things we've been working on that you might know about. So one of the things is discrete element method. So you have a bunch of particles which are basically non-intersecting spheres. And the idea is, so this is called the discrete element method. And why it's been used is it's been used to study asteroids. Okay, so why do we want to study asteroids? Because one's about to hit the Earth in 2029, or not quite hit the Earth. So this is a phantom simulation of asteroid Apophis. So this is the Earth, this is the Moon, and the asteroid is coming in from the bottom right here. This is 2029, the 11th of April. The passage happens on Friday the 13th. These two are the rush limit, where the thing would be completely disrupted and like destroy all life on Earth. Thankfully, Apophis will not destroy all life on Earth, but it goes mighty close and nearly hits the Moon as well. And so understanding the response of an asteroid to a near-Earth collision, that's a really bad simulation. It's just a bunch of test particles. So we'd like to do a better job. This is a project that's ongoing this year where we're simulating this with these discrete elements. So these are currently sync particles, but the plan is to make them into SPH particles. But this is actually Apophis. You can't see Earth in this video, but Earth is in the background. And we spun it up a little unrealistically just to make things come off it. But you can see various scenarios where Apophis is encountering the Earth and doing violent things to the asteroid itself. Probably won't happen. Apophis is spinning much slower than that, but who knows? What we'd like to do is simulate stuff like this. So like they're called granular flows, like a sandcastle. The physics is kind of complicated, but right now we're working on sort of the large boulders and have large discrete objects, and we'd like to fill it with sort of SPH particles in between representing the kind of regolith. So we've got a few projects in that direction. If you're interested, come and talk. There's lots of things being worked on that you're going to hear about this workshop. But again, we're going to make our own list anyway. So that's all for me. Thanks.